This is the module on atmospheric rivers. I'm Ed Zoke, and Dan Bikos and I put this together. Here are the learning objectives. We'll be using the new imagery, RGBs, and products from GOES 16 for an atmospheric river event that hit California in March 2018. It is important to note that because we need to look well off the west coast, with GOES 16, we will have to use full disk imagery, which has lower horizontal and temporal resolution than conoscale imagery. Just to briefly review, an atmospheric river is a relatively narrow swath of high moisture extending from the tropics or subtropics into mid-latitudes. So of course it can lead to heavy precipitation events. Now most often we think of them as west coast events, but they can be found in the Gulf of Mexico and off the Atlantic as well. And the effects can extend far inland. Some references for further information are shown here. What's new in the GOES-R era to help us with atmospheric rivers? In terms of qualitative evaluation, there are 3 water vapor channels versus just 1 previously, as well as new RGBs and data from the Global Lightning Mapper. For quantitatively evaluating an atmospheric river, we want to determine the amount of precipitable water, or PW, in the AR plume. Polar orbiters provide the operational blended total PW product, as well as a new advected layer PW product that we will look at. GOES-R also has a PW product, and we will demonstrate that product and how it differs from the polar products in this module. Here's a brief review of the March 2018 event we'll be looking at. We show the 2-day stage 4 precipitation, which was considerable, over 5 inches and even close to 10 inches in the mountains, with the precip extending quite far inland and very heavy snows over the higher elevations. This turned out to be a significant event, as we can see from these weather story pages from some of the affected WFOs. Hit the pause button if you would like to look at these further. Here is a long 10.35 micron IR loop at hourly intervals so that we can show the entire event. The color table is IR color cloud winter. Because this is GOES 16 in the GOES East position, we see that image resolution goes down as we move westward into the Pacific. GOES 17 was not available for this March 2018 event, but would be the satellite of choice with better resolution in its GOES West position. There are 2 main intrusions of moisture into California and the western U.S. in this loop. The first is at the beginning of the loop on the eastern side of the upper level low that is stalled well offshore. After a slight break, we see the second surge. This is a new tropical connection of moisture into this surge coming off the ITCZ in the southwest corner of the imagery. This moisture combines with the main plume as it all moves onshore. The event starts to end as the overall trough pushes eastward. In the next few slides, we will be examining the first day and a half of this loop with various GOES 16 bands, RGBs, and products, in particular focusing on the second surge of moisture. This loop uses a 4-panel AWIPS display to show the 3 water vapor channels that are available on GOES 16 and 17, compared to only 1 before GOES-R, as well as a new product called the Air Mass RGB. The default color table is used for the water vapor imagery called Ramsdis Water Vapor 12-bit. The lower level water vapor channel is in the upper left, mid-level channel in the upper right, and higher level water vapor band in the lower left. Since clouds have sufficient moisture to quickly saturate the water vapor channels, we generally see similar brightness temperatures with the clouds in the atmospheric river plume in all 3 water vapor channels, except somewhat colder for the higher level water vapor channel. Of course, because the cloudiness saturates all 3 water vapor channels, we cannot use water vapor imagery to determine much about the atmospheric river once it is filled with clouds. But we can still use the imagery to gain some information. For example, notice how the initial moisture surge into California at the beginning of the loop appears first in the higher level water vapor band, well before we see it in the lowest level 7.34 micron imagery. This tells us that the initial moisture coming on shore was at higher levels and not very thick, and indeed rain did not begin along the coast until 08Z on 20 March. Another area where the water vapor imagery is helpful for this event is in showing the surge of moisture moving northward from the SatFC-G that was noted earlier, seen here in the lower left portion of each panel. This time the northern edge of moisture and cooler brightness temperatures is similar for all three water vapor channels, implying more than just higher level moisture at the leading edge of this surge. The reason we can see this surge so well is that the area has only partial cloudiness initially, with more widespread cloud cover not coming until later. The air mass imagery shown in the lower right panel uses some of the water vapor and IR channels to highlight different air masses and also cloud top heights in a single image. It can be useful to identify the different air masses present, and for our case also nicely shows the second northward moving moisture plume. We might also want to look at other RGBs that use water vapor channels, such as the differential water vapor RGB and the simple water vapor RGB. Here's the same 4-panel loop, but with GFS analyses interspersed with 3-hour forecast overlaid on the lower two panels. We have 300 millibar isotachs with the higher level water vapor imagery in the lower left and 500 millibar heights on the air mass imagery in the lower right. With the 500 millibar height overlay, we can get a better idea how the different colors of the air mass imagery are related to the troughs and ridges. The core of the strong jet in the Pacific overlays nicely with the warmer brightness temperatures in the 6.19 micron water vapor imagery, with the atmospheric river on the anticyclonic side of the jet. Here we have the same water vapor imagery in a 4-panel loop, but now in the lower right panel we display a new GOES-R product, the GOES Total Precipitable Water product. GOES TPW is a legacy atmospheric profile, or LAP baseline product, derived from the 3 water vapor channels on GOES-R with a 10-kilometer horizontal resolution. The GOES TPW product is available at 5-minute intervals, although here we have 15-minute intervals since we are on a larger scale. A limitation of this product is that TPW is derived only in clear or nearly clear sky conditions, as can be seen in this loop where the blank or black areas correspond to clouds in the water vapor imagery. However, note that unlike the water vapor imagery, we get a quantitative measure of the moisture present. The limitation with respect to clouds does not allow us to determine the PW within the AR plume, and in this loop we have focused on the northward surge of moisture. Specifically, note the northward push of the red and bluish colors in the far southwest portion of the image during the first part of the loop, showing the deepening moisture to levels at and above 2 inches of TPW moving northward before cloudiness develops. In this 4-panel we have zoomed out, and now the same GOES TPW imagery is in the upper left with the IR 10.35 micron imagery below it. In the upper right is another GOES-R baseline product that would be of use for AR events, the GOES rain rate or QPE product, displayed as a rate in inches per hour. There are some known problems still being resolved with this product, and it is expected to become more accurate, but one can see the potential value with rain rates shown well off the California coast beyond radar range and within the atmospheric river plume. Another baseline product is shown below this in the lower right panel, the cloud top height product, which is most effectively used in concert with the IR imagery. Both these products are discussed further in separate modules. This loop is shorter than the previous loops during the period when the AR plume had spread well inland. While we lose a lot of information in the GOES TPW product in the cloud-filled atmospheric river, note how you can still get glimpses of the TPW in fairly small areas where there is some temporary clearing. Since the GOES TPW product has no information in areas of cloudiness, one could combine the product with some type of cloud imagery, as seen here where band 2.64 micron visible imagery has been used for this shorter loop on 22 March. Instruments aboard some polar orbiting satellites allow for TPW to be measured in both clear and cloudy conditions, with data dropout possible in areas of precipitation. Here we show the longer loop again, with a 4-panel where the blended TPW product that has been available on AWIPS for some time is in the lower right panel, compared to the GOES TPW in the lower left panel. The lower and mid-level GOES 16 water vapor imagery are shown in the top 2 panels. The TPW scales differ somewhat, mainly for values below 1 inch. While the aerial coverage is much better from the blended TPW product, the time resolution is worse, and the horizontal resolution is 16 kilometers. But the obvious advantage of the blended TPW is the ability to measure the precipitable water within the cloudy areas, including the core of the atmospheric river. A more recent TPW product derived from polar orbiting satellite data is the layered precipitable water, or LPW product, which separates the atmosphere into 4 layers from the surface through 300 millibars. Shown in this loop is a newer version of the LPW product called the advected LPW product. More information on these products is available in a quick guide found on the Visit website, and the product is available experimentally to WFOs for display on AWIPS 2. Contact myself or Dan Bagos on how to get this imagery into AWIPS. There are occasional areas of no data when satellite coverage was incomplete. Otherwise, these smaller areas of no data are regions of precipitation. This loop covers the entire event, and we can see several of the features discussed earlier, as well, of course, as the distribution of PW in the vertical within and near the AR plume. Data from the Global Lightning Mapper was not operationally available for this March case, but it would be useful for AR analysis in terms of identifying particularly active convection within the plume. Here is an example of the GLM flash extent density product from GOES 16 on AWIPS for a different modest atmospheric river event into Central California in the west on 28 November 2018. The GLM shows some active convection in the cold frontal band to the north that was merging with the AR plume. We have overlaid it on Band 2 visible imagery from GOES 17, hence the higher resolution imagery off the west coast. In summary, the GOES-R series aids in atmospheric river identification and analysis qualitatively by using information from some of the new band's products and RGBs, and quantitatively by using other products such as the GOES TPW product or the rain rate product. Of course, using information from the GOES-R series in concert with polar satellite products that show total precipitable water or the new ALPW product can help paint a more complete picture.